All right, so let's continue on here, and now we will cover hypothesis tests, our favorite topic here. Okay. So here we have hypothesis tests for mu based on a sample. Okay. All right, and so this time, when we write our hypotheses, so a lot of the principles that applied to hypothesis tests for proportions apply here as well. Okay. The key difference happens in kind of the calculations. The formulas change for the calculations, but that's not too big of a deal because you can just write them down on your formula sheet and you're fine. Okay. And then when we look up our p-value, we use the t-table, which behaves fairly differently from the z-table, or I shouldn't say behaves, but just works in a different way. Okay, but if you recall, for hypothesis testing, we had kind of 4 steps, and so we said step 1 was to make your hypotheses, right? Okay, and so the hypotheses for the population mean mu, we will still have a null hypothesis and an alternative hypothesis, okay? The null hypothesis always has what? An equal sign, okay? And this time we're not talking about p, we're talking about what? Mu. We're talking about mu, but good, okay? So we're talking about the population mean mu, and it's going to be mu is equal, and it's going to be some number, okay? So I'm going to, just for kicks, I'll just write 30 here, okay? But, you know, whatever number we have, it's symbolically, it would be mu is equal to some number, and we would write mu 0. But this often confuses students because this looks like we've got 2 symbols going on. But really, it's just mu is equal to some number here, okay? And then the alternative is identical to the null hypothesis, except we replace the equal sign with something else, right? So we have mu is not equal to 30, or mu is greater than 30, or mu is less than 30, or something like that, okay? Again, not necessarily 30, but some number there. Some constant called mu 0 here. Okay, so just to kind of, throughout this, as I'm defining things, I'm going to just use mu 0 equal to 30, just so we don't get confused here. Okay, is this all right? Okay, so of course, when you read the problem, it's going to say, like, is the average, or is the mean different from, you know, 620? Then you would plug in 620 here, or something like that. Okay. All right, step 2. What do we do in step 2? Yeah, we check the conditions, okay? And again, like I said, as far as quiz problems go, I'm going to have the conditions already met, okay? But I will have kind of a separate section where you check your conditions, okay? So you check your conditions, and then you pick your alpha, or identify the alpha to use. And if alpha is not given, what do we use? Okay. Yeah, so the default alpha is 0.05, okay? It's not too bad, right? Okay. Step 3, we're going to calculate our p-value. Okay, and that consists of 3 subparts. So 3a is get your standard error. And that's going to be S. The standard error is equal to S over the square root of n. The standard deviation of the sample divided by the square root of n. Okay? And then what's the next thing we do? We get our test statistic. Okay? And the test statistic is kind of the difference between the reality and the expectation, right? So here, our test statistic is not z, but it's t is equal, and we're going to use x bar minus the value mu 0. Okay, so in our case, mu 0 is 30 or whatever it is, and we're going to divide this by our standard error. Okay, and then lastly, once you have a test statistic, what do? You look it up in the table to get your p-value, right? Look up the test statistic in the table to get a p-value. Is that okay? All right, so this part is significantly different, so I'm going to devote the next kind of slide or sheet in our lecture to looking it up and getting a p-value, okay? But as far as kind of like how this hypothesis test works, it's quite similar to how the other hypothesis test works, right? I'm hoping we feel that way. Okay, and then lastly, once we have our p-value, what do? We make a conclusion, right? And how do we make our conclusions? Yeah, so at this point we just compare the p-value to alpha. So the conclusion only depends on the comparison between the p-value and alpha. Okay, it doesn't depend on anything else. So if the p-value is greater than alpha, we what? If the p-value is greater than alpha, we do not reject the null hypothesis. Okay? And we don't say we accept the null hypothesis. We just say we do not reject the null hypothesis. And on the other hand, if the p-value is less than alpha, we reject the null hypothesis. We do reject. Yeah, this is it almost never equal to, but I guess if I had to put the equal sign, I would put it over here. But I would just say greater than alpha. But I don't know. It's tough to say. Okay. This is what we have. All right. So I'm hoping.
What about not equal 2 times? Something that here or no? Or is that for 2 samples?
That the whether you have the greater than, the less than, or the not equal sign comes into play for step C. Okay, because here once you get your p-value, you just compare the p-value to alpha, whether you have the double-sided or not. Okay, so
It's not equal. It was 2 times. When
the 2 times thing, that is either not equal, greater than, or less than in the alternative. That comes into the getting the p-value. Okay, the 2 times, whether you do multiply it by 2 or not, that comes into play in step 3C. Okay, getting your p-value. But once you have your p-value, then it's just you either reject the null or you don't reject the null. Okay, and that applies to hypothesis tests for proportions or hypothesis tests for means, 1 sample or 2 samples, all of that stuff. Okay. Yes.
I'm sorry, just to go back on that, what you saying, the double thing,
Uh-huh.
only when you look up the z score and then you subtract, you go 1 minus the z score and then you get that, and then you multiply that answer by 2?
That if you have an alternative that has a not equal sign, then your p-value is 2 times the tail area. Okay, and that involves looking up the z-score. And if your z-score is negative, then you just double what's in the table. If the z-score is positive, then you do 1 minus the area, and then you double it. Okay? Yeah, okay. But we're good here, right? This is good? Okay, so what's changed between this and for proportions? The hypotheses are different, so you're using mu, and you've got a number here rather than p in some proportion. Okay? And over here, your standard error is s over the square root of n. And then your test statistic is x bar minus mu 0 divided by the standard error. Okay? Okay. All right, so let's talk about looking up the test statistic to get a p-value. Okay? So this, we're going to use the t-table. Okay? And so I'm going to just like copy part of this here. So the way it works is you've got your test statistic. Okay, so let's say you do in step 3b, you get your test statistic t equal to 2.41. Okay? We're going to look up 2.41 in this table, but we first need to figure out how many degrees of freedom we have. Okay? So this is, I'm saying, like, you've done all the other work, you got your standard error, you plugged in, plugged it in to get your test statistic, and so at the end of step 3b, you get a test statistic of 2.41, okay? And so now we are trying to go from the test statistic to a p-value. Is that okay? All right, so the things you need to know. So you need to get a p-value. To get a p-value, you need your test statistic t. That's why I'm... Okay, you need the alternative hypothesis, okay, so whether it has a greater than, less than, or not equal to, okay, and then you also need your degrees of freedom, okay. So these are the 3 things you need, okay. So we have our t is equal to 2.41. Let's say our alternative hypothesis is mu is greater than 30. And let's say we have degrees of freedom. How do we get degrees of freedom? N minus 1. So let's say we had, n equal to 12. We would have 11 degrees of freedom, right? Okay, is this good? Oh, huh? Okay, so what we're going to do is we go to the row with 11 degrees of freedom. I'm going to just kind of underline it right here. Okay, so I've got 11 degrees of freedom. And so these are the only numbers that matter here, okay? And what I'm going to do is I'm going to come here and I'm going to look up, try to see where 2.41 fits, okay? And I'd say 2.41 is in between 2.201 and 2.718. Can you guys see that? Are you guys looking at your table? 11 degrees of freedom, 2.4 is in between 2.2 and 2.7. Okay? And so what that means is I go to the top of the table and I see t 0.025 and t 0.010. Okay? And so that means the corresponding tail area is between 0.025 and 0.010. Okay? Is that okay? So I'm just going to the top of the table where it has, t 0.025 and t.010, okay? So this is basically 2.5% and this is what, 1%, okay? So I mean, this is 0.025 and 0.01, right? Okay, and so what we say is my tail area, so this is what we have so far, and so here, because the alternative, HA, has a greater than sign, okay, our p-value, well, I'll say a few things. Our test statistic, t, should be positive. If you get a negative thing, there's a slight problem, okay? So if the alternative has a greater than sign, your test statistic should be positive, okay? And then your p-value is between, your p-value is equal to the tail area. So in this case, we say our p-value is between 0.025 and 0.01. Okay? I know it says 0.010, but you generally don't keep trailing zeros after a decimal point, right? Yeah.
It says the tail area between 0.25 and 0.010. What's
The tail area or the p-value?
No, the tail area. So the tail area is between 0.025 and 0.010.
Yeah.
What do you mean between? You mean those two added divided into 2? You mean the mean of that?
No. So it's between these. So because my number 2.41 is between these two numbers, my tail area is also going to be between these two numbers. Okay? If my t ended up exactly 2.201, then my tail would be exactly 0.025. Okay? But we almost never get something exactly this value, right? If I ended up exactly at 1.796 and I had 11 degrees of freedom, then my tail is exactly 0.05. Okay? But here, because it's 2.41, it's between these two numbers, and that means my tail is between these two numbers here. Okay? Is that okay?
Yeah.
All right, let's try another one. Okay? So let me just kind of list off a few things. So we'll say if HA has a greater than sign, then T should be positive. I'm going to put plus positive. I'll just write should be positive. And then your p-value is equal to the tail area. Okay. If the alternative has a less than sign, the t should be negative. Okay? And then what you would do is you would ignore the negative sign and just look up the positive value in the table, because the table only has positive values. Okay? So then you say ignore the sign, ignore the minus sign, okay? And then your p-value is equal to the tail area. Okay? And if the alternative has a not equal sign, okay, look up the t, okay, and then your p-value is equal to 2 times the tail area. All right, is that okay? Yeah, so we'll do more examples like this, okay? Yeah, question.
So the first two, it's gonna have like the same answer, right?
Yeah, you just look it up, and then your p-value is the tail area, whatever's in between the column headings.
Because if we're ignoring the negative, then won't it just be a positive, just like the first one? No, right?
Yeah, exactly. It'll work the same way. It's just you should end up getting a negative sign. Okay. All right. So let's say, so scenario 2, your test statistic ends up being negative 3.025, 3.61. You have degrees of freedom equal to 7. And your alternative is mu is less than 46. Okay, what is our p-value? Okay, well, first of all, what's our tail area here? We would go to 7 degrees of freedom, right? I'm sorry. With I guess n is equal to 7, so we have n is equal to 8, so we have degrees of freedom equal to 7. Okay, so I have 7 degrees of freedom, and so what's my tail area?
0.005 between 0.005 and 0.001.
Exactly. And because I have a less than sign, my p-value is my tail area, right? So here I would say my p-value is between 0.005 and 0.001. Is that okay with everybody? Just want to make sure everyone's okay with this. Question?
It's saying, I'm sorry, it's saying the tail area is between, it's saying the p-value is between.
Well, in this scenario, because I have a less than sign, so I should say my tail area is between 0.005 and 0.001, okay? And then because, so over here, if I check, my p-value is equal to the tail area, all right? My p-value is equal to the tail area. We have a question?
Oh, yeah.
Yeah.
So either whether or not it's positive or negative or greater than or less than sign, it's always just the tail area other than a not equal sign, right?
Yeah, okay. All right, so let's complicate things just a tiny bit, okay? Well, because these scenarios happen, all right? Let's say your t ends up equal 13.4. You have degrees of freedom equal to 12, and your alternative is mu is not equal to 10. Okay, so we're looking at 12 degrees of freedom. T is 13.4. What do we do there? Okay, so 13.4 is way bigger than 3.93, right? Or it's just bigger. Whether it's way bigger or just a little bit bigger, it doesn't matter, okay? What we have is that I'm going to just put 13.4 is over here, okay? So that means my tail area is what? Well, before I do, no, my p-value is 2 times my tail area, okay? Because I've got this, but what is my tail area? Is it, how does it compare to 0.01? 0.001. My tail area is less than 0.001. Is that okay? So if you look, as the numbers get bigger this way, the tail area shrinks as we go this way. So we have small tail values over here and large tail values over here.
So you don't know what is in between, you just know that it's less than 0.001.
Exactly. We don't have an exact value, but we do know for sure that it's smaller than 0.001. That's exactly right.
If it's less, then you just keep it as is. Like, you don't multiply it by 2, right?
Well, no, we still do. Okay, so my tail area is less than 0.001, okay? Because the alternative has a not equal sign, we're going to say my p-value is 2 times the tail. So what do we end up getting? We get the p-value is less than 0.001 times 2. So it's going to be 0.002. My p-value, whatever it is less than 0.002.
So the T is usually given.
No, the t, you're going to have to do all of the calculations. I'm just saying, you know, you're doing, in the process, you've come up with a hypothesis, you check conditions, you figure out your standard error, your test statistic, and then once you have your test statistic, how do you get your p-value? And I'm saying, before you had the z-table and you would just look it up in the z-table, and you guys knew how to do that, okay? But the t-table works different from the z-table, and that's why I'm spending time focusing on just how to use the t-table. Okay, all right. Is this okay? Yeah.
The same thing as like 0 point something.
Yeah, let's try one more example here, okay? Just to kind of cover all of our bases.
So just to clarify, what is usually given in the question that requires us to use this table?
You'll be given a mean, a standard deviation, and a question asking that you're going to have to use to figure out your hypothesis test, okay? Let's focus on this. We'll do an example, okay? And you'll figure out what kind of stuff is given. Okay, so last one, we'll say t is equal to 0.94, okay? And you have degrees of freedom equal to 10. And let's say your alternative is mu is not equal to 7, okay? Okay, so in this case, we're at 10 degrees of freedom, and 0.94 is smaller than 1.372. Okay? Huh?
So do you multiply that?
So, well, first of all, tell me what my tail area is. My tail area is greater than 10%, right? 0.100, according to this. Are we okay with this? My tail area is greater than 0.1. And because I have a not equal sign, my p-value is 2 times the tail area. Okay, and then so what I conclude is my p-value is greater than 0.2.
How do you get the 0.1 tail area is greater?
So I look up 0.94, and we see that 0.94 is less than 1.372 in the row for 10 degrees of freedom. I go to the column heading of 0.1, and we see that, you know, I've got to be on this side of 0.1. So I'm going to be greater than 0.1 because larger values are to the left. For the column headings, we got larger values over here and smaller values over here. For the critical values, or the test statistics, smaller values are on the left and larger values go on the right. Is this okay?
Wait, can you explain that again? For the, I got kind of confused on it being greater than.
Why the tail area is greater than 0.1?
I would assume that it's less than. but
Okay,
I'm not sure
so you just have to look at the column headings, and we see that on the left is large and on the right is small. If you look at the column headings.
Is that always going to be the case for this table?
Yeah, I mean, this is the table, right? I'm not going to be changing it up on you. So yeah, at the column headings, large numbers are on the left and small numbers are on the right. Okay, so if you're to the left of something, you're bigger than this one, and if you're to the right of this, you're smaller than this one. Okay, otherwise you're in between the two column headings. Yeah.
On the quizzes and tests, we'll just be given degrees of freedom for values that are on this table, right? We're not going to be given like a 35.
Oh, okay. Yeah, no, that's a very good point. Thank you for bringing that up. If you're ever given a degrees of freedom that does not appear on the table, to be safe, we always round down. Okay? So if you're given 39 degrees of freedom, you would round down to 30 degrees of freedom. Okay? You would not, even though 40 is closer to 39, you would round down just to be safe. Okay? It's like, huh? It could happen. It could happen. Okay? So always round down your degrees of freedom. And that's, now some people might disagree with that, but huh? Like like if you look at your table, right? So we're missing values like 31, 32, 33, and things like that, okay? So let's say you have 38 degrees of freedom, okay? Normally, if you were trying to round to the nearest number, 40 is closer to 38, okay? But that would be rounding up. So we want to round down, and we would go to 30 degrees of freedom, okay?
So even if you have 48, you go to 40.
Correct, okay? Even if you have 1,000,000 degrees of freedom, you should, according to this table, round down to 100 degrees of freedom, okay? And because infinity is actually way farther away from 1,000,000 than 100 is from 1,000,000, okay? So, all right, so let's try an example here. Okay, so someone claims that, I don't know, the average cost of a gallon of milk I don't know, is $3.50. I don't know if that sounds reasonable or not. Okay. That's what someone claims, okay? You're like, I don't know if I believe you. Okay. So to test this claim, you obtain prices of, I don't know, 10 randomly selected milk gallons. What oh, I don't know how to speak. Okay. All right, so you get, anyway, you go out and you get a sample of 10 things, okay, and then you figure out you're right, and like, so for example, like one place had it for like $3.06, and another place had it for like $4.50, and another place had it for $3.79 or whatever, et cetera, et cetera, et cetera. Okay, you get 10 values. Okay, so the average of these 10 values, we'll say the average price was $3.65. Okay, and the standard deviation in price was 45 cents. Okay. So we're going to say okay, yeah. So does your data provide evidence that the cost of a gallon of milk is not $3.50? Okay, so here it's just saying is not. So figure out your hypotheses. You know what? In the interest of time, just because we're covering so much stuff, I'll just do this all, okay? But I'll talk through it, and you can just promise me you'll pay attention and learn and review your notes, okay? Okay, so well, what should our hypotheses be?
Sorry.
So we're going to say mu is equal to 350, okay? And our alternative is mu not equal to 350, okay? So we got mu is equal to 3.5 and mu is not 3.5, okay? All right, so we're going to check conditions, and I'll just say the conditions are met. I mean, maybe they're not, but we're going to pretend like the conditions are met. Okay, so let's, I guess this is step 2. And then step 3. Okay, so step 3a is our standard error, which is s over the square root of n. So I would plug in 0.45 divided by the square root of 10. Okay, so I got 0.45 divided by the square root of 10, and I got 0.142. All right. Step 3b is getting our test statistic. T is going to be x bar minus mu 0 divided by our standard error. So what's my x bar? 3.65. What's my, here, you know what, sometimes what's very helpful is just labeling these numbers. So we have 3.65 is x bar, 0.45 is my s, and 3.50, this is my mu 0, okay? And then 10 is going to be my n. Okay, so sometimes, so I often recommend when you see a problem to go and just label each of these numbers with their correct labels so that when you plug them into the formula, you don't accidentally use the wrong number. Okay, okay, so I got 3.65 minus mu 0, which is 3.5, divided by 0.1423, something like that. Okay. All right, so we're going to have 3.65 minus 3.5 divided by, and I'm going to hit the answer key, 0.142, and I get 1.054. My t is equal to 1.054. Okay, what should I do now? We're going to go to the t table. How many degrees of freedom do I have? 9 degrees of freedom, and we're looking for 1.054. So my tail area, according to the table, my tail area, go to 9 degrees of freedom. The first number is 1.383. 1.054 is smaller than that, so my corresponding tail area is greater than 0.1. Okay? Is my p-value the tail area, or do I have to double it? I have to double it, right? Because I have a not equal sign. So HA has not equal sign. So my p-value is 2 times the tail area, so I get my p-value is greater than 0.2. Yeah?
I know for the p-value, you multiplied the tail area, right?
I multiplied the tail area by 2.
Okay, because the hypothesis has a not equal sign, right?
Correct.
But if it's a greater than or less than, you still have to multiply by 2 to get the tail value.
No. If the alternative had a greater than or a less than sign, then my tail area, my p-value is the tail area.
Okay,
So then I would just say my p-value is greater than 10%. Okay? Yeah.
Just to clarify, on our t table,
Yes.
values are greater than 0.1. We say p-value is greater than 0.1. When it's less than 0.001, we say p-value less than 0.001.
Correct. Yeah. So here I've got my p-value is greater than 0.2 because I've doubled my tail area. We have another question.
So 9 given in 3C.
Huh? 9 degrees of freedom? Where did I get that? So degrees of freedom is n minus 1. Okay, what's n? 10. It's my sample size. Okay, so I do n minus 1. Okay? All right, so my p-value is greater than 0.2. All right, so let's say step 4, we're using alpha equal to 0.05. So we have alpha equal to 0.05. So we don't know exactly what our p-value is, but we do know that it's greater than 20%. So we have our p-value is greater than alpha. Okay, so we would say do not reject the null hypothesis. Okay, and what does this mean? We have or do not have evidence. Okay, so we do not have evidence that what?
The price of milk is not $3.50.
Yeah, we do not have evidence,
You have a lot of English majors in here.
yeah, that the price of milk, or that the average price of milk, yeah, thank you, that the average price of milk is not $3.50, okay? Does that mean the price of milk, average price of milk is $3.50? No, okay? That's why we have to use this double negative stuff, okay? It doesn't prove that the average price of milk is $3.50. It's just, you know, you went out and you looked at 10 gallons of milk and you're trying to make a conclusion about the average price of milk. Well, I'm sorry, this is not enough evidence for us to really say anything, okay? All we can say is we don't have evidence that it's not $3.50. Yeah.
So the probability of it being,
We can't,
3.50 is 0.05, right?
no, we can't talk, so the p-value is a probability, but what this is saying is that, you know, if the average cost of milk truly is $3.50, whenever I go out and take a random sample of milk prices, I've got over a 20% chance that the average is going to be $3.65 or something more extreme, okay? But it's not, we can't say there's a 5% probability or 20% probability of something happening, okay?
Yeah, so if it's less than the alpha,
If the p-value is less than alpha, we would reject, okay? And then we would say we do have evidence that the average price of milk is something other than $3.50, okay? So we do say that. All right. Are we feeling okay about this?
Yes.
Kinda?
No,
Kinda, okay. Yes?
If our p-value is between 5% and 2.5%,
Yeah.
what's the conclusion?
Yeah, so, yeah, okay. So the only problem would be if your test statistic ended up exactly one of these column numbers, okay? But that's almost going to never be the case. Let's say you have, we had 9 degrees of freedom, and we end up 1.85, okay? At 1.85, we're in between these two columns, and our tail area is in between 0.025 and 0.05, right? That means our p-value is less than 0.05. Okay, if our p-value is between 0.025 and 0.05, it's less than 0.05.
It cannot be never be.
The only time our p-value would be equal to 0.05 is if we happen to get the exact number that shows up on this table. And that happens very, very, very rarely. It could happen, but it's very rare, okay? You know, because you would need this number exactly, okay? And if you get that exact number, then you would have a p-value equal to 0.05, okay?
So why don't you say that the p-value is greater than 0.025 instead of saying it's less than 0.05? Instead of saying it's less than 0.05, why don't you say it's greater than 0.025? Can you make that conclusion?
I'm sorry, I'm not sure if I understand your question.
Right now that the p-value is greater than
What are you referring
the
to?
example that you were just answering.
Okay.
That if it's in between
Yeah, we'd say it's
1.85. It's
Okay.
between the point. It's between 0.05 and 0.025, right?
Yeah, we would say our p-value is between 0.05 and 0.025. Yeah. That's what we would say.
specific number within the.
Yeah, we would just say we don't, you know, we don't know exactly what the p-value is, but we do know that it's between these two numbers. Okay, and that's all we need to know. Because really, all we need to know is it bigger than 0.05 or is it smaller than 0.05? That's really all we care about. Or is it whatever alpha you've chosen? Is it bigger than that or is it smaller than that? So yeah, if you've decided to use alpha equal to 4%, 0.04, then you'd be in trouble, okay? Because we don't know, and you get like 1.9, we don't know, okay? So don't use an alpha equal to 4% because our table only gives us for 0.05, 0.025, or things like that, okay? So, Okay. I hope this is okay, and we'll continue on here. We still have 2 topics, but again, because everything is kind of parallel to each other, I feel like we can cover each of these, give 15 minutes to each of them, and we'll be okay. If you disagree, you know, we have a week dedicated just to review also, okay? All right, so we're going to do confidence intervals for the quantity for mu1 minus mu2, okay, based on 2 samples. Okay, so this time we are comparing 2 samples and we are making inferences about their respective populations. Okay, so essentially we look at 2 samples and make inferences about their respective populations. So we want to know, do the 2 populations have different means or not? Okay, so I'm going to just kind of throw this here. So the confidence interval for mu1 minus mu2, okay, in the middle, we're going to put the best guess that we have for mu1 minus mu2. So our best guess for this quantity would be x bar 1 minus x bar 2. Okay, this is our kind of the best guess that we put in the middle. And then we're going to go plus or minus a critical value times the standard error. Okay. Our critical value, because we're dealing with means, is going to be t star. And then the standard error is just going to be this ugly formula, okay? So anytime you have two samples, the formulas get a little bit ugly, all right? So it's going to be s1 squared over n1 plus s2 squared over n2, all inside a square root, okay? But if we just say this is the standard error, we recognize all the same pieces. We've got the best guess that we have for whatever it is we're making a confidence interval for. We throw in a critical value, and we got a standard error. Is that okay? Okay. For the degrees of freedom is equal to n minus 1, okay? But we have 2 n's, okay? So we have 2 n's, okay? n1 and n2, right? So you're going to use the smaller n, okay? So use the smaller n. For your degrees of freedom. And this is it, okay? And often questions will ask, do we have evidence that there is a difference between the population means, okay? Okay, do we have evidence that there's a difference between the population means? And our answer is if 0 is inside the interval, then it's plausible that our population means have no difference, okay? So then we won't have evidence, okay? So if 0 is inside the interval, okay, it is plausible for there to be no difference.
What do you mean by 0 is inside
The value 0, is it, you got a lower bound and an upper bound, right? So if 0 is in between the lower and the upper bound, then 0 is inside the interval, okay? On the other hand, if 0 is outside the interval, okay, it is not plausible for there to be no difference, so we would say we do have evidence that there is a difference. Okay, we got this? Not yet. No. That's how my hand feels every day. Like, my whole life I'm just, well, it used to be, I had to write on, I would write on the chalkboard, and then it'd be like my shoulder would be killing me at the end of like a long day of lectures, like my shoulder would be killing me. And then before I got mic'd up, I would have to be yelling, and I'd come home and I'd be like, like I wouldn't want to talk to anybody, like, so the tablet and now writing is like way better. Yeah, my hand gets tired, but it's not so bad. And then having the mic is a lifesaver also. Okay, let's try an example here. Okay, so here's a silly question: are men on average taller than women? Okay, or is there a difference between the average height of men and women? Okay, so this is kind of a little silly because we already know the answer is yes, right? Like I don't think anyone's gonna object here. Okay, so we got two samples. We'll say sample 1, and what you call sample 1 and what ends up being sample 2, whether it's sample 1 is the men or sample 2 is the women, or the other way around, sample 1 is the women and sample 2 is the men, it doesn't matter, okay? So what shall sample 1 be? Women, of course, okay. And then sample 2 will be the men, okay? All right, and then so we're going to have what is the average height? Well, okay, let's say we've taken, I'm sorry, let me start off with N1. So how many women did we observe for our random sample? 40. That's a lot. Okay, let's. Okay, but sure. Okay, let's do. All right, we'll say 28. Sure. Okay, and then how many random men did we look at? It doesn't matter. We'll say 20. All right, sure. Okay, and then what was the average height of these 28 women that we observed? 5'4". Okay, so we'll say 64, we'll say 0.1 inches, okay? And what was the average height of these 20 men that we looked at? 5'11". So we'll say 70.6 inches, okay? And then the standard deviation we'll say was 3.1, and the standard deviation over here we'll say is 3.5. Okay. Yeah, I would probably write it out, but for the interest of time, I'm gonna say it like this. But it would not be hard to write this out, right? It would say like you looked at a sample of 28 women the average height of those women was 64.1 inches with a standard deviation of 3.1 inches, right? It's just now in sentence form, okay? But so basically, when you're presented with a question, you're going to have to extract and say, this is N1, this is X bar 1, and this is S1, okay? So I will not present it to you in a problem all nicely formatted like this, but I think if you read, that's a skill that you need to have for this class, okay? If you can do it for one sample, you can do it for 2 samples. Okay, so let's make our confidence interval. So we'll say we'll make a 95% confidence interval, okay? All right, so our 95% confidence interval is x bar 1 minus x bar 2 plus or minus t star times our standard error, which is s1 squared over n1 plus s2 squared over n2. Okay, let's figure out what our t star is. How many degrees of freedom will I have? Degrees of freedom equal to n minus 1, but I've got 2 n's and I'm going to use the smaller one. So I have 20 minus 1, 19 degrees of freedom, exactly, okay? 19 degrees of freedom, 95% confidence, 2.093. Great. Everybody good with that? Okay. So now it's just a matter of just plugging in numbers. Okay, x bar 1, 64.1 minus x bar 2, 70.6 plus or minus t star 2.093 times the square root s1 3.1 squared over n1 28 plus s2 3.5 squared over n2 20. Okay, I'm going to just so I'm going to do this part before the plus or minus first. So 64.1 minus 70.6, I get negative 6.5 plus or minus, and I've got 2.093 times the square root, and inside that parentheses I've got 3.1 squared divided by 28 plus 3.5 squared divided by 20, and I'm going to close off this square root. Okay, and I'm going to hit enter, and so this comes out to be 2.046. All right. Can everybody use their calculators, I'm hoping? All right. So I've got negative 6.5 plus 2.046. So on the high end, I have negative 4.454. And on the low end, I've got this minus 8.546. Negative 8.546.
So in this case, the t value is equal to the exact one that we see, right?
Yeah, because here my t is, I'm looking up the t in the table and I get this. Yeah. Okay. Is this okay? So this is just the calculations. All right, so let's do the interpretation. I would say I am 95% confident that the average height of women is between, and I've got negative 8.5, I'm negative 8.55 basically, and negative 4.45 basically here, okay? So I'm going to just write is between 4.45 inches and 8.55 inches shorter, because they're negative, right? Shorter than the average height of men. Are we okay with going from our interval to our statement here? Okay, so Our interval is 0 inside our interval. No, our entire interval is like really negative, okay? So 0 is not in the interval. And so what that means is we have evidence that that there is a difference between the average heights of men and women. Okay. Now, if we had labeled sample 1 to be men and sample 2 to be women, okay, pretty much all of the numbers would be exactly the same, except they would all be positive. Okay, and it would be from positive 4.454 to positive 8.546. Okay, and then technically the statement would just change to I am 95% confident that the average height of men is between 4.45 inches and 8.55 inches taller than the average height of women. Okay, so whether you say on average women are shorter than men or on average men are taller than women, you're saying the same thing. Okay, are we good here? Okay, all right, last topic. I know you guys are so excited for this one. Okay, hypothesis testing for mu1 and mu2 based on 2 samples. Okay, all right, so step 1, so the same 4 steps for hypothesis testing. So make our hypotheses. The null hypothesis is mu1 is equal to mu2. So it's always going to be this, and then the alternative will be mu1 is not equal to mu2, or mu1 is greater than mu2, or mu1 is less than mu2. Okay? It's just like when we were dealing with proportions. We had 2 proportions and 2 samples and all of that. Same type of stuff. Step 2. Prepare, so we check our conditions. And identify alpha. Okay, or the default is alpha equal to 0.05, same as before. Step 3, okay, calculations. Okay, so 3a is our standard error. Okay, standard error, because we have 2 samples, it's just this thing, s1 squared over n1 plus s2 squared over n2. (3b), our test statistic. T, do you guys recall what it was for proportions? It was p hat 1 minus p hat 2 over SE. Here it's x bar 1 minus x bar 2 divided by the standard error. Okay. Okay, what's the next step? Yeah, look it up in the table. Look up in the t-table to get a p-value. Okay, and this works exactly the same way as it did when we did hypothesis testing with 1 sample. Okay, we're gonna look it up in the t-table to get a p-value, and here again, degrees of freedom is equal to n minus 1. Use the smaller n. use the smaller of n1 and n2. So you've got two n's, and use the smaller one. Okay, and then last thing, step 4, make your conclusion. Same as before, right? P-value greater than alpha, that means do not reject the null hypothesis. And the p-value is less than alpha, reject the null hypothesis. It's not so bad, right? Right? Like you've seen hypothesis testing like, I don't know, a bunch of times by now, and so this follows the exact same thing. The only thing that has changed here, you've got this standard error, okay? And then you're gonna use x bar 1 and x bar 2, and you're gonna do this, but everything else works the same. I almost feel like we don't even have to do an example, and you guys will be fine, right? Huh? Yeah, you guys just want to get out of here, right? We have a question.
I think it's gonna be confusing to find those to know like which one.
Yeah, exactly. So we will spend time during our week before the final, the review week, on how to figure out exactly which one to use in which scenario. Okay, because that's a key thing. Okay, that's it. Have a good week. We'll see you guys next Tuesday.